Hello, everyone. Today we continue to solve some problems about vector spaces, fields, and different things you learned during the last week. I still can't solve your homework for you. I think the due date is not it's not due yet, actually. So so I'm going to solve some similar problems for you. Okay. Is there any question, any mathematical question from things that we've discussed up to this point or things that the professor um, has discussed in the class? Okay, if not, let's start by solving some problems. If you remember any question, you can unmute yourself and ask me. Okay. So, as you know by now, the main focus of the course is on the vector spaces, right? And fields. But here we mostly take our field to be either the set of real numbers or the set of complex numbers. So here, suppose our field is F and our vector space is V. Mhm. So one very common example for our field, for our fields is R. And then a very common example of the vector spaces we work on are the Euclidean vector spaces, Rn, where n is a natural number. It's 1, 2, 3, etc. Right? Now, I like to consider one specific case. Consider the case where n is equal to 1. So here, our field is the set of real numbers, and our vector space, again, is the set of real numbers, right? Here, R is a vector space over itself. Now, I want to do something. I want to consider something a little bit exotic. Suppose as a field, also, please join the meeting before the start of the class, okay? Otherwise, you would miss things I've said in the beginning of the class. Okay, so I want to do something a little bit exotic. Suppose our field is R, the same real numbers as we know it, but our vector space, which again is R as a set, is a set of real numbers. It is R, but I want to define a new addition on this set. So I want to change the algebraic structure of the vector space. So in order to not confuse between R as a field and R as a vector space, I keep on using F for the field and V as the vector space. Note that as a set, both of them are just real numbers. Now what I want to do is that this vector space, V, which is just R, the vector space, as we know, it is supposed to be equipped with addition, right? For any two elements, U and V, in the vector space, we should define addition. So I should define what is U plus V, right? Because it's not the usual addition, I would slightly change the notation. Rather than writing plus, because usually we know what plus what it means for real numbers, I write plus, I use this notation, plus inside a square, okay? That's my new addition. I'm going to define this new addition. I would define it to be the maximum, the max of, well, note that U and V are just real numbers. Although I'm using an arrow because they're elements of my vector space, they're just numbers. They're just real numbers, like 2, -1, pi, things like that. So I would define it to be the max of U and v. So for example here, 2 square plus 3 would be just the max of 2 and 3, which is 3, right? That would be my addition. So that's when I'm talking about my vector space, it is the set of real numbers. But the addition here we are defining is not the usual addition we have on the set of real numbers. It's this new one. I'm just calling it an addition. It's not the usual sum as we know it. Okay. Now vector space has a second operator. Vector spaces have a second operator. The second operator of a vector space was scalar multiplication. So remember, we can take an element in the field, which here field is again the set of real numbers, and an element in the vector space, which again here the vector space is the set of real numbers. And then we have scalar multiplication, which means we can multiply the vector, our vector, by the scalar. Again, because there is a usual one, which is just the product as we know it. But because I want to define a kind of different way of multiplying vectors by scalars, I use a slightly different notation. I use a dot inside the square. I define this thing to be, well, let's first start, let's not make it very complicated. I would just define it to be the usual thing, just the usual multiplication. Again, remember, although the role of alpha and u, the roles are different, one of them is in the field and one of them is in the vector space, both of them are real numbers. So I can just simply multiply them, right? Now, the question is that with this definition, I said I want V, the set of real numbers, to be a vector space over F, again, the set of real numbers. But is it true with this new, with these new operations, B, the set of real numbers, F, the set of real numbers, this new addition I have, and this usual scalar multiplication? Is this thing really a vector space over the field F or not? So with these new definitions, is V a vector space over F or not? Let's just answer this question because we talked about this one. I want to get to another point from this question. Let's not spend a lot of time on that. Maybe think for 1 or 2 minutes and then tell me if you know what is the answer. Okay, now let me answer it. So yeah, I can see in the chats that we have some correct answers. Okay, yeah, that is correct. Now let me summarize that. So the first property of vector space is when we define this addition, is the first thing is to think about is usually associativity. So let's see if that holds here or not. U plus V, say plus W. The question is that, is it equal to U plus V plus W? Okay, so is that correct or not? So let's see. On the left-hand side, it means first we should compute the max of U and V as two real numbers. Just as two real numbers, we should see what is the maximum of these two numbers. And then look at W and see what is the maximum of the max of U and V and W. Well, this is simply just the maximum between these three numbers, U, V, and W, right? So for example, let's say we have 1, 2, 3. It doesn't matter if we first say what is the max between 1 and 2, well, which is 2, and then computing max between 1 and 3, which is 3. So the whole thing, the max is 3. It doesn't matter if we do that or first we compute max of 2 and 3 and then with 1. So we do have associativity. So the first thing really holds. Okay, so the first property is correct. So what is the next thing? The next thing is having identity element for the addition. So is there some element which if I add u to that element, I would always get u? So that's what we mean by identity element. So in ordinary addition, we have 0. If we add 0 to any other number, we would end up with 0. But do we have the identity element here? Is 0 the identity element or not? Does anyone know the answer? Do we have?
I don't think there is one.
Can you explain again? Sorry, I had muted my PC. I just noticed that. Can you?
Yeah, I don't think there is one because for any number that you could think of, you can always choose one less. The only thing would be negative infinity, but that's not in R.
Mm-hmm. That is correct. That's exactly correct. So this is correct. So for any number u, anything you think about, any other number you think about, you say v. U plus v would be max of u and v. And we want this to be equal to u for any u. Remember, this v should work for all different numbers like u. But that never works because well, if u is just v minus 1, max of u and v is max of v minus 1 and v, which is v, and it's not u. So this operation really doesn't have the identity element. There is always something which is smaller than v. And so also your comment is correct. So as we know, plus infinity and minus infinity, these are not elements of real numbers. They are not real numbers. 1, 2, 3, these are real numbers. Plus infinity and minus infinity, they are not real numbers. But if for a second, just for a second, if we assume they are, if we just assume that, actually minus infinity would work as the identity element here. So for any u, that's what matters. For any u, u plus minus infinity is max of u and minus infinity. But anything is larger than minus infinity, right? Minus infinity is smaller than all real numbers. So the max is always u. So u plus minus infinity would be u, and that's correct for any u. So sometimes people call this new set R. It get this point, we get to a new definition. Sometimes people add minus infinity, or sometimes even plus infinity to the set of real numbers, just for the sake of this property. It's related to some subfield of algebraic geometry, which is called tropical geometry, which we would then talk more about that. But here we don't have that, so we don't have the identity element, so no identity element. So it's not a vector space. We can continue to see if other properties also, if they hold or not, but because we just found one property which does not hold here, this set is not a vector space. in the comments I see some other properties which do not hold, and they are correct. There are other properties of the definition of vector space which does not hold here. Okay. Any question here? Okay, so if not, let's continue. Okay, let's slightly think about. Well, let's raise the dimension. Let's say the field F here again is R, but the vector space V again is R2, but again not the usual R2 as we know it. Again, it comes with a different definition. So for any U and V, two vectors inside this vector space, I would define U plus V. Again, let's again put it in square. I just mean it's not the usual addition as we know it. Let's define it like this. So note U and V, these two vectors are in R2. So both of them, they have two components, X component and Y component, U1, U2. Also, V is an element in R2, so it can be written as V1, V2. Okay, now let's define this addition to be U1. Well, the addition is supposed to be again another element of R2, so again it should have two components. I define the first component to be U1 plus V1 plus 1, and the second component to be U2 plus V2 plus 1. So if we didn't have these plus ones at the end, that would have been the usual addition which we have on R2. But right now, it's because of these extra plus ones, it's different. And then for any element alpha in the field, which is again R, and for any vector U in our vector space V, I define alpha times U again to be the usual scalar multiplication. We just multiply each component of U by alpha. So it is the usual one. Again, let's think just for a minute to see if this definition gives us a vector space or not. Okay, think for a second to see if we get a vector space here or not. Does anyone have the answer? You can unmute yourself and say it if you think you know if this is a vector space or not.
I would think no, because there's a problem with the 0.
Mm-hmm. Okay, yeah, and also in the chat, I see someone has said not distributive. Okay, let's see that. So let's again, the easy thing usually to check is the identity element. We are looking for an element like 0. I would show it with O. I'm not sure if it's the 0, 0 in R2 or not. I'm looking for an element in V such that U plus that element is just U. Now, this identity element, O, it's supposed to be something in R2. So it has two components, X and Y, right? Therefore, U plus O would be U1 plus X plus 1 and U2 plus Y plus 1. Correct? We want this thing to be equal to, what do we want? We want this thing to be equal to U, right? So we want, what do we want? What we want is that we want this to be equal to the vector U. The vector U, again, has two components, U1 and U2. Now, if these two things are supposed to be equal, each component should be equal to the corresponding component in the other vector. That means u1 plus x plus 1 should be equal to u1, and u2 plus y plus 1 should be equal to u2, correct? So what we want is that we want u1 plus x plus 1 to be equal to u1, and u2 plus y plus 1 should be equal to u2. Actually, these equations really tell us what is this vector O. Because in the first equation, we can cancel u1 from both sides. Therefore, x plus 1 should be 0, which means x is equal to minus 1. And the second equation, similarly, we can cancel u2 from both sides, and y plus 1 would be 0, which that means y is minus 1. Now, the vector O, the identity element, it was x and y, which is simply minus 1, minus 1, negative 1, negative 1. So yeah, that's correct. We have the identity element. So although in the first glance you guessed it might not have the identity element, actually it does. So here, in some sense, the 0 element of this vector space is not 0 and 0, it's minus 1 and minus 1. So it has the identity element. Okay, the other thing someone has suggested is to see if it's gonna distribute, if the multiplication would distribute over addition. So what does that mean? It means if we take two, well, there are two things to consider. Oh, it seems we have a counter example. Let's see. So someone has said consider these vectors. Say u to be 1 and 1, and v to be the vector 2 and 2, and alpha to be 3. For a vector space, we know alpha times u plus v should be equal to alpha times u plus alpha times v. Let's see if this equation holds here or not. If it doesn't hold for this specific piece of information, these two vectors and this number, then we have a counter example, and therefore it's not a vector space. Okay, what is u plus v? U plus v is going to be 1 plus 2 plus 1, and 1 plus 2, plus 1, which is 4 and 4. If you multiply this result by alpha equal to 3, you would get 12 and 12. Actually, I guess, well, let's see. Now, on the other hand, alpha times u is equal to 3 and 3. Alpha times v is equal to 6 and 6. Alpha u plus alpha v, alpha u plus alpha v is equal to 3 plus 6, which is 9, plus 1 is 10. 3 plus 6 again is 9, plus 1 is 10. And we can see these two things are not equal. 12, 12, and 10, 10, they're not equal. Therefore, we don't have the distributive law, the law of distribution. So it's not a vector space. Again, not a vector space. Yeah, okay, that's pretty good. Okay, now we talked a little bit about matrices. That's the direction I want to go now. So something we saw the other time was that the set of n by n matrices of real numbers, so the set of n by n matrices of real numbers with the component-wise addition, which when we have two matrices, we just add the corresponding components to each other. They form a vector space over the real numbers as a field. Okay, just so with the classical addition of two matrices, which we would add each component to the corresponding one in the other matrix, we would get a vector space. Now, again, what I want to do here, I want to define a new addition, which is not the usual one. I would define this addition to be 1/2 of 1/2 of a times b plus b times a. And here times is just the ordinary multiplication of matrices for all a and b to n by n matrices. And then I would define, let me just ask a question. Is everyone familiar with the way we multiply matrices together with matrix multiplication? Does anyone want me to explain it? Okay. So if you need me to remind you how we would do that, you can just ask. And then for any alpha in our field, which is the set of real numbers, we would have alpha times a matrix. Well, the usual definition is we would multiply each component of a matrix by that real number. Okay, here we changed that definition to, I would define this multiplication to be the matrix 0 for all alpha and all a. Okay, just 0. And again, the question is that is V with this with these new definitions of addition and this scalar multiplication, is it a vector space or not? Space or not? Okay, think about this one again for 1 or 2 minutes. Okay, so, okay, let me write down the answer. So yeah, obviously, one of the problems with this scalar multiplication is it doesn't have the identity for multiplication. So one property of one part in the definition of vector space over field is that if you take the identity element in your field, 1 times any vector here, which is a, should be equal to a itself. But here, our multiplication is defined to be 0. And if a is a non-zero matrix, it's not 0. Therefore, this identity does not hold. That's one difficulty. That's one problem here. That's correct. So it's not a vector space. Let's look at some other things. For example, let's see if we have associativity here or not. Okay, let's see if a plus b plus c is equal to a plus b plus c. Okay. Now, a plus b is 1/2 times ab plus ba. Now, the whole thing plus c is equal to 1/2 times what we have here in the parentheses, the whole thing times c, which would be 1/2 ab plus ba times c, plus c times the whole thing there, which is 1/2 AB plus BA. Now, if we simplify this thing a little bit, we would say it's equal to 1/4. Okay, here we have AB times C, so we get ABC plus, sorry, the second thing here is BA, BAC, and then we have CAB, and then we have CBA. So that's the result of first adding A and B and then C. That's what we would get. Okay, I would compute the other one just here, so we would have both of them on one page, and we can compute that. So what about A plus and then B plus C in parentheses? Okay, so we have A plus. B plus C is 1/2 BC plus CB, right? And then A plus that is equal to 1/2 A times whatever we have here, which is 1/2 BC plus CB, plus, again, the whole thing here, 1/2 BC plus CB times A. Again, here we can simplify this thing a little bit. We would get 1/4 times A times BC, which is A, BC, plus A times CB, which is A, CB, plus BC times A, which is BCA, plus CB times A, which is CBA. Now the question is that are these two things in the blue rectangles, are they equal or not? Okay, here we have ABC, here we have ABC, here we have ACB, right? Do we have ACB down there? No. Here we have BCA. Do we have BCA down there? No. Here we have CBA. We have CBA down here. But if you look at the rest of the things here, we end up with ACB plus BCA. But down here we have BAC plus CAB. And are these two things equal or not? If they're equal, we would have the equality. If they are not equal, well, we don't get associativity. So probably, as you know, the matrix multiplication is not commutative. So in general, AB is not equal to BA. We can't change the order of the multiplication. So the question here we should answer here is that is 1/4. So oops, sorry. ABC plus ACB plus BCA plus CBA. The question is this thing equal to 1/4 ABC plus BAC plus CAB plus CBA. Well, for a second, assume they're equal. Let's see what we would get to. If we assume they're equal, let's start from this equality. Let's suppose we have associativity, and let's see where the associativity will get us to. So if they're equal, we can multiply both sides by 4. We would get rid of these two 1/4 factors. We would cancel ABC from both sides. We would cancel CBA from both sides of the equation. And then we would get ACB plus BCA is equal to BAC plus CAB. Okay, so I don't know if these two things on right side and left side are equal or not. One way to try to test that is what we call trying to find a counterexample. Trying to find a counterexample. That means if I find three specific matrices, A, B, and C, which they do not satisfy this equation, then this equation is not correct in general. Okay, so let's try that. Let's just randomly take three matrices. So we were working on n by n matrices. We can make everything special. Let's say n is just 2. So when you're looking for a counterexample, you should try to make everything as special as you can, so it would simplify things. So we would choose three 2 by 2 matrices. Okay, let's just say 1, 2, 0, minus 1, 0, minus 1, 1, 2, and let's it be 3, minus 1, minus 1, 2. We have three explicit matrices. Let's compute these two quantities. Let's see if they are equal or not. Okay. So on one side, we have ACB. ACB. ACB is equal to 1, 2, 0, minus 1 times 3, minus 1, minus 1, 2 times 0, minus 1, 1, 2. Okay, first I would compute the multiplication of the first two matrices. The result is 3 minus 2, which is 1, minus 1 plus 4, which is 3, 1, and minus 2. And then I should compute the multiplication with 0, minus 1, 1, 2, which is 3, minus 1 plus 6, which is 5, minus 2, and minus 1, minus 4, negative 5. Okay, that's ACB. The second thing we have is BCA. BCA is equal to 0, minus 1, 1, 2. That's B. C is 3, minus 1, minus 1, 2. And A is 1, 2, 0, minus 1. This thing is equal to plus 1, 2, 3 minus 2, which is 1, and 4 minus 1, which is 3, times 1, 2, 0, minus 1. This is equal to 2 minus 2, which is 0, 1, and 2 minus 3, which is minus 1. So the sum of these two is the quantity we have on the left-hand side is 4, 5, minus 1, minus 6. That's the thing we would get on the left-hand side. Now we should do the same computation for the right-hand side. We should see what would be the result of right-hand side. Okay, let's do that. So I would get rid of these computations. Maybe I would start from, maybe I would write here. Okay, so BAC is equal to 0, minus 1, 1, 2, 1, 2, 0, minus 1, 3, minus 1, minus 1, 2. So the multiplication of first two matrices is equal to 0, 1, 1, 0, times 3 minus 1, minus 1, 2, which is equal to minus 1, 2, 3, minus 1. And then we have CAB is equal to 3 minus 1, minus 1, 2, 1, 2, 0, minus 1, CAB, 0, minus 1, 1, 2. The multiplication of first two matrices is 3, 6, plus 1 is 7, minus 1, and minus 2, minus 2, minus 4. Times 0, minus 1, 1, 2, we would get 7, minus 3 plus 14, 11, it would be minus 4, 1 minus 8 minus 7. And then if we add these two matrices here, what we would get is 6, 13, minus 1, and minus 8. And as you can see, these two matrices are not equal. So we have a counterexample here for this associativity. If it doesn't hold in a special case, it doesn't hold in general. And that's another thing. So we don't have associativity. A very good technique is usually to find counterexample when you guess something is not correct, some property does not hold. Just focus on something specific. Okay, any question here? Okay. So if not, let's continue. Okay. Let me see if there is any question. Okay, so let's continue with a little bit more about subspaces in the last 5 minutes. You might be familiar with some of these. So we talked about the notion of subspace. So suppose we have a vector space V. Suppose we have two subspaces, U1 and U2. There are two subspaces of V, okay? Now, there are a few questions I want to make sure if you know these or not. One is, consider U1 intersection U2. It means the vectors which are both in U1 and in U2. Is this is still a subset of V, right? Is this a is this a subspace itself or not? Is this a subspace of V or not? Okay, you can just tell me if you know the answer. So we have two subspaces. We take the intersection of them. Do we end up with a new subspace or not? Mm-hmm. Okay, we got one yes. Or yeah. The answer is yes. So remember, what is the definition of a subspace? We had some different things. It should be closed. It should be a vector space itself. It should be closed under the addition and scalar multiplication. So that's the case. So for example, let me just write down a few of them. So if I take some U and V, two vectors, inside this intersection, for example, I should show what I want to show is that their sum is still inside this intersection. That's one property I need to show to say this intersection is a subspace. So is that correct or not? So because U and V, the way the argument goes is that because they are in the intersection of these two spaces, it means they are in both of them, right? When we have two elements in the intersection of two sets, it means they are both in U1 and U2. So the small u would be in U1, and at the same time, this element is in U2. Same thing holds for the vector V. It's in U1 and the vector V is in U2. Now, the assumption tells us that U1 and U2 are subspaces. So they are closed on their addition. So if U is in U1 and V is in U1, their sum is in U1. It means U plus V is in U1. Same thing holds for U2. If U is in U2 and V is in U2, because U2 is a subspace, the sum of these two is in U2. So U plus V is in U1 and also is in U2. Therefore, it's in their intersection. When we have something inside two sets, it's in their intersection. So U plus V is in U1 intersection U2. You should prove the same thing holds for scalar multiplication. For example, the argument is completely similar. So yeah, it is a subspace. What about the union? If U1 is a subspace and U2 is a subspace, is the union a subspace of V or not? Is that the case? The answer is no. So we can see that maybe pictorially. So for example, let's say R space is R3. Say U1 is this plane here. U2 is this plane here. Their intersection would be this line, which is a subspace. But the union is union of this plane and union and the other plane. And this is not a vector space. Why? Well, this element here is something in U2, so it is in the union. This element here is in U1, so it's in the union. So U and V are in the union of U1 and U2, right? So their sum should be in the union. But what is the sum of these two vectors? The sum of these two vectors is something, for example, here, which is obviously is not in the union of these two spaces. It's outside of them. Okay, so the answer here is no, and it's very simple to construct a very simple counterexample. When one of the spaces is this one and the other one is this one, the sum of some element here and some element here wouldn't necessarily fall into the union itself. It would fall somewhere outside. So this is not a subspace. You can think about the same question for U1 plus U2 to see what is the answer, for example, for that. Is that a subspace or not? That's also an important question. Okay, is there any question? Okay, I think time is up. I would wait here. If you have any question, I would answer, okay? Oh, what is the addition of subspaces? Okay, I would just explain that as the last thing. So as a set, it means all the vectors of the form U plus V, where the first vector is in the first space and the second vector is in the second space. So each of these two subspaces, they have a lot of elements. Look at all elements in U1 and all elements in U2, okay? They're vectors, you can add them. And look at all these additions. The set of all of them is U1 plus U2. And if you haven't seen this before, it might be a little confusing. So let me just explain a little bit more than this. You can leave if you want. The class is officially over. But if you are not familiar with this, you can stay to listen. So I'm assuming U1 and U2 are two subspaces of another vector space V. And I want to see if their addition, in the sense that I told you, you would add all the elements in U1 to all elements in U2, is a subspace in V or not? Is this thing a subspace? That's the question. Okay. So some of the properties of the subspace. It should contain 0, right? Any vector space should have 0. Well, because U1 is a vector subspace, it has 0. U2, because it's a vector subspace, it has 0. And U1 plus U2 is the sum of elements in U1 and elements in U2. So 0 from U1 plus 0 from U2 is an element in U1 plus U2. But 0 plus 0 is just 0. So the 0 vector is in this subspace U1 plus U2. That's one thing. The other property is that if I take two vectors in U1 plus U2, if I take two vectors, U and V, I should show U plus V is there. That's the second thing. Is that correct or not? Well, U is in U1 plus U2. Anything in U1 plus U2 is equal to something in U1 plus something in U2. So U itself can be written as, say, A plus B, where A is in U1 and B is in U2. So note that any element in U1 plus U2 is equal to something in U1 plus something in U2. So if U is there, we should be able to write U as something in U1 plus something in U2. I call them A and B. Same thing holds for V. If V is in U1 plus U2, we should be able to write V as C plus D, where C is in U1 and D is in U2. Now here we have U1 plus U2, right? So U1 itself is A plus B. And V is C plus D. Okay, I changed the order. I can do that, right? Because we're in V, in vector space, we have associativity. I would write it as A plus C. Sorry, commutativity, actually. That's what I'm using. Plus B plus D. Now, A plus C, note that both A and C are in U1. And U1 is a vector subspace. If A and C are in U1, their sum is in U1. On the other hand, B and D are in U2. U2 is a vector subspace, so their sum is in U2. Now, what can we say about this whole sum? The first part is in U1, the second part is in U2. By definition, their sum is in U1 plus U2. But this thing was equal to what? It was equal to U plus V. So U plus V is in U1 plus U2. We should do the same thing for other properties, and we can see they all hold. And actually, U1 plus U2 is the smallest subspace which has both U1 and U2. Okay, we should check that for scalar multiplication, etc. Okay, any other question? Okay, if no, we can stop it here. Thank you. Okay, bye.